Hello and welcome back. All right, so we're going to continue looking at comparing two groups. All right, so last time it was comparing two groups with proportions. Today it's going to be comparing two groups with means. So the top of these notes say condor versus bullet. And what we would have done is we would have been making paper airplanes. I don't know why I'm telling you this. It's just like rubbing salt in the wound. But we would have been making paper airplanes, and one of the models was called the Condor. One of the models was called the Bullet. All right, so we would have all made paper airplanes. We would have gone out into the hallway. We would have thrown those paper airplanes, and we would have measured how far each model went. All right, and what we were investigating is, or what we would have been investigating is there a difference, and when I say difference, I mean a significant difference in the distance that the Condor travels versus the distance that the Bullet travels. So basically, is one airplane better than the other, or are they basically equivalent? Are they going to fly about the same distance? So we would have gathered information, we would have gathered some data, and then we would have done some calculations on that. So again, I apologize. I can't apologize enough. But here we are. All right, so is the difference we found in the average flight distance significant, or could it have been by random chance? All right, so this is kind of the process that we're going to go through. All right, so when it says write our hypotheses, all right, so the only difference between this and the proportion is that we're going to be using the symbol for mean. So we could say the null is that the mean of the Condor would be equal to the mean of the Bullet. And then the other way we could write this, just like with proportions, we could write, so I'll put or there, we could write UC minus UB equals 0, which is just another way of saying that there's no difference between those two means. And then our alternative, again, if we were in class, I would have had you speculate which one do you think is going to go further, which ones do you think is going to go less far. Usually the assumption is that the Condor is going to not go as far, so the Condor is going to be inferior to the Bullet. So the alternative that we might write is that UC is less than UB. And actually that's technically be mu. That's the Greek mu there, lowercase mu. So there are null and alternative, and again, this one could be written as UC minus UB is greater than 0. All right, so suggesting that, whoops, not greater than 0, sorry, less than 0, because we're saying that the Condor is smaller than the Bullet. So we could have also said that we could have written it this way, and either one of those is fine, whichever way you prefer to write it. Usually people pick this way just because it's shorter, but you should just know that if you see it one of these two ways, it's equivalent. And then again, we're testing with an alpha of 0.05. So, you know, we gather our data, we compare it to what we should expect, all right, because this curve that we're analyzing it against is based on there being no difference. All right, so this curve is based on being that there's no difference. And then if we end up down here on this curve, all right, at this extreme, you know, this represents 5% of the curve. This is our rejection zone. If we end up in that part of the curve, then we say there's a significant difference, all right? It's unusual to end up in this part of the curve, so when it happens, we say that, you know, there's a good chance that this curve is wrong, and there's a significant difference between the two of those. All right. So, as usual, the conditions need to be in place. So, it should be randomized, whatever your experiment is. It should be independent. And if you don't have true independence, you should make sure that your sample is less than 10% of the population, just like we've been saying all along. And then with this one, the distribution should either be normal or n should be greater than or equal to 30. So if they're normal, you don't have to worry about the sample size, but if they're non-normal or you don't know if they're normal, then n should be greater than or equal to 30. And this applies to both samples. So again, we've got two different samples that we're comparing here. Both of them should have an n greater than or equal to 30. And then you want to have independence between groups. All right, so there should be no obvious connection between the two different groups. If there is a connection, if they're not independent, that's when we have paired data. And that's where you use the one variable test with the differences. And I'll show you what I'm talking about in a second, but let's just put that note there. If you have paired data, use a one variable test on the differences. All right, so if you have paired data, use a one variable test on the differences. And that's what we did back in the last unit. So here's just an example from the notes from the last unit where we had data. There were two different groups. So this was like our June group, this was our August group. But there's obviously a connection between these two groups because it was the same people. Like this was one person taking the test in June, this was the same person taking it in August. So these two groups are not independent. So instead of using each group separately, we take the difference of those two groups, so this minus this, and then do the test just on those differences. All right, so when you don't have independence between the groups, you do the test on the differences. When you do have independence between the groups, we're going to do this two variable test that we're about to walk through right now. So again, just you have to know based on the situation which test you should be using. And basically this is the determining factor, whether or not you have independence between the groups or not. All right, so again, the sampling distribution that we're going to be using is based off the mean from the first sample minus the mean from the second sample, very similar to what we did with proportions. We're going to have this combined standard deviation, which again comes from the same rule that we learned about combining standard deviations and random variables. You square the standard deviation, then you add them together, and then you take the square root, just like we did way back when. And again, the center of this sampling distribution is going to give us sort of the true value there. All right. So let's take a look at how this would actually play out. All right, so sample statistic. So again, we're just going to make up some numbers here because we didn't actually have sort of the chance to do this. So let's just pretend we have a bullet average, and we'll say that on average that went, we'll just say 35 inches. And we have a condor average. And let's just say, again, we're just making up numbers here, that went 20 inches. All right. So again, we're not concerned as much with the individual averages. We're concerned with the difference between those two averages. So again, the difference is pretty simple here. It's just 35 minus 20 for a difference of 15 inches. And what we're testing is we're testing whether or not this gap right here is significant. Whether this 15 inches is large enough that we can say there's a significant difference between the two airplanes, or whether that 15 inches is small enough that we chalk it up to random variation. Right? You know, if we did this experiment again, maybe it would be 15 inches in the other direction. If we did the experiment a third time, maybe it would only be 2 inches. If we did the experiment a fourth time, maybe it would be 3 inches in the other direction. But, you know, is this 15 inches large enough that we can be totally confident that the Bullitt is the better paper airplane? All right, so we're also going to need the difference of means from the null hypothesis. Now remember, the null hypothesis assumes they're the same. So if we were to look at the Bullitt average minus the Condor average, that would just work out to be 0 because the null hypothesis assumes that those two things are the same. Right. So standard deviation, all right. Again, if you know the population standard deviation, which we never do, we would use a normal distribution. Again, we never really have that information. All we ever have is the sample standard deviation. So we're going to use the t-distribution just like we have been for the last couple of units. All right. So again, this is in theory. If you had this information, we could use the normal distribution. But in reality, we never do. So we use the t-distribution here. Now, again, really quickly, just so that you can see where this formula is coming from, all right, this has been the formula that we've been using for means. All right, now technically that's the population standard deviation. Usually we're using the sample standard deviation, but either way, this formula should look familiar. So the variance, because again, if this is the standard deviation, the variance is just this formula squared, which would give us this right here. Now remember, the variance is what we actually add together. All right, so we could take these and we could add these together. We could say, all right, we're doing this from our first sample and we're adding it to this from our second sample. All right, we can combine the variances. That's allowed. And from way back when, even though we're subtracting these, we still add the variances. And then the last step is always to take the take the square root to turn it back into a standard deviation. All right, and that's exactly this formula that you're seeing right up here. So it's not a mystery where that comes from. It's just a result of the rules we have for combining random variables. All right, so again, we're just going to make up some numbers here so that we can do this. So let's pretend that the standard deviation for the Bullitt, we'll just say that it was, I don't know, 8.5 inches, and we'll pretend that we had 20 throws of it. So this would be 8.5 squared. And then we'll pretend that for the Condor it was, why don't we just say 4.2 inches, and again that's squared, and again we'll pretend that there were 20 throws. So again, I'm just kind of pulling those numbers out of thin air, but they work for our purposes here. And then we could, put this in our calculator. 8.5 squared divided by 20 plus 4.2 squared divided by 20. All right, that gives us that, and then we can't forget to take the square root at the end. And we get a final answer of 2.12, we'll say. All right. So next question is, with t-distribution, is how many degrees of freedom do we use? So the conservative option is to do n1 minus 1 or n2 minus 1 and use whichever one is smaller. So in our case, both of our n's were 20, so 20 minus 1 is going to give us 19, and that's what we'll be using when we do this out. Now, when your calculator does it, it actually uses this larger formula to calculate degrees of freedom. This is not a formula you need to know. It's never a formula we're going to do by hand. But when we start doing these two sample tests on the calculator, the degrees of freedom that it uses is actually not based off of this. It's based off this larger calculation, which gives a more accurate measure of the degrees of freedom. All right, so again, just something to know that this is what we're going to do for the by hand example. But when your calculator's doing it, it's actually using this much more involved sort of calculation there. All right, so now that we have our sample statistic, we have our expected difference from the null, we have our standard error, we can calculate our test statistic. All right, again, that's kind of the way these all go. Now, because we're doing the t-distribution instead of the normal distribution, we use t instead of z. But remember, it's the stat minus kind of your hypothetical, which is coming from the null. All right, remember, this is coming from your null. It's your hypothesized difference over the standard error. So again, our t was 15. That's what we observed. The expectation was 0. And our standard error was 2.12. All right, so we'd calculate that out. 15 minus 0 divided by 2.12 and end up with, let's just say, 7.0755 equals 7.0755. All right, which is pretty large. All right, that's like 7 standard errors above what we'd expect. So now we just have to turn that into a percentage and kind of see what that gives us. So our p-value here, we're going to use, instead of NCDF, we're going to use TCDF. All right. Our statistic, our test statistic that we just calculated was 7.0755. And we want to know what are the odds of getting that statistic or higher. Remember, generally, if it's positive here, you're going to go above. If you end up with a negative test statistic, generally you're going to go below. All right, but we ended up with a positive one, so we're going from this to positive 9999. And then our degrees of freedom are going to be 19, because again, that's coming from the 20 minus 1. All right, so we can go to our distribution menu. We can go to TCDF. We can say 7.0755 to 9999 with 19 degrees of freedom. All right, and notice this e to the negative 7. You've been missing this a lot, but that e to the negative 7 means this is actually 0.1, 2, 3, 4, 5, 6 zeros, and then 4937. So it's a very, very small number. So in this case, we reject the null and accept the alternative. All right, and if we go back, our alternative was that the condor was less than the bullet, or if you read this backwards, that the bullet was greater than the condor. So there is a significant difference the bullet goes further than the condor. All right. Again, this right here is under 5%. That's what we're always checking. We're checking how it compares to our threshold value. All right, so we are going to see that we can do this on the calculator. All right. Now there's a note that it says when using the calculator, we never choose the pooling option. This assumes population variances are equal and is mostly a relic of time before computers. All right, assuming the population variances is equal just makes the calculations much, much simpler. But that's something we don't really have to worry about anymore, so we don't do it. But when we go and do one of these on the calculator, again, we're going to choose t-test, not z-test. You are going to see, oops, sorry, not t-test, stat test. Two sample t-test because we have two samples here. All right, t-test is when there's just one sample. So two sample t-test. You are going to see down at the bottom, there's an option for pooled, no versus yes. We're always going to pick no. All right, never pick yes for this. The choice is always going to be no. All right, so that kind of walks you through what the process is for these two sample t-tests. All right, you gather your data, you find the observed difference in the means. All right, so there's our observed difference. You compare that to the expected difference, which is always 0. You calculate your standard error using this formula. Using all of those pieces, you calculate a t-statistic. That t-statistic is compared to the t-distribution. All right, we find what percentage we're dealing with, and then based on that percentage, we either reject or fail to reject our null. All right, so again, that's the general process that we're going to go through. Yes, we're going to move to just doing these on the calculator, but this is the process the calculator is going through. Everything we just did by hand is exactly what the calculator is going to be doing when you go and choose two sample t-test. All right, the whole process we just went through is exactly what the calculator is going to be doing. All right. Okay, so let's kind of continue on with the same process, but instead we're going to look at how we would do a confidence interval, also sort of the long manual way. All right, again, we will learn how to do it on the calculator, but I want you to have an appreciation for what the calculator is actually doing. All right, so again, the general formula that we're going to be using is you're going to start with your sample statistic, and then we're going to be adding or subtracting a critical value times the standard error. All right. Now, most of these things you've actually already calculated. All right, so our point estimate, or kind of our starting point for the interval, is what we observed in our experiment. So in our experiment, we saw a difference of 15 inches. So that's what we're going to be using here. We'll start with our point estimate of 15. The standard error is what we calculated down here. It's where we combine the standard deviations from our two different samples. And we ended up with this value right here, so 2.12. All right. So the only thing that's left to find is our confidence level. All right. So this is where we're going to be using inverse t. All right, because again, it's not inverse norm because we're dealing with a t distribution here. So on your calculator, if you go to the distribution menu, you should have inverse t. Oops, let's clear this out. Distribution inverse t. All right, so it wants to know the area. Now again, if you're doing a 95% confidence interval, that means there's 5% left over, but that 5% gets split up between the left side and the right side. So our area is only going to be 0.025. All right. So again, there's 5%, but then that gets split between 2.5% on the left and 2.5% on the right. All right. So we've got our 0.025 there. Degrees of freedom, again, is your sample size minus 1. So we would use the smaller degrees of freedom. Again, the calculator is going to do something more sophisticated when we actually use the test menu. But for right now, we can just use degrees of freedom of 19. All right, and that's going to give us a critical value of negative 2.09. But again, we sort of ignore the negative, and we just say that that's going to work out to be, so actually, just let me write this here. So it's inverse t of 0.025 with 19 degrees of freedom, which is going to work out to be 2.09. Right. So again, we've seen this before. Right? It's the same setup. It's just, you're getting your numbers from slightly different places. So we already found the standard error when we did the hypothesis test. So I'm not going to redo the calculation. It's the same exact calculation we did right here. All right, I just showed you how we end up with the critical value. So that's this 2.09. All right, so the only piece that's left is just kind of plugging all of those numbers together to get your final answer. So it's basically going to be 15 plus 2.09 times 2.12, and it's going to be 15 minus 2.09 times 2.12. All right, so again, that's just some calculator work there. 15 plus 2.09 times 2.12. All right, gives us 19.4308. All right, and then 15 minus 2.09 times 2.12 is 10.5692. Okay. So again, what these numbers represent is that we are 95% confident the true difference, and it's always a good idea to say what order you did the subtraction in. So if we go way back here, all right, when we calculated this 15 inches, we got that by doing bullet minus condor. So we are 95% confidence the true difference of bullet minus condor is between 19.4308 and 10.5692. All right, so we think the gap could be as large as 19.4 inches, or it could be as small as 10.5 inches. But we're pretty certain that, the bullet is going further than the condor. All right, so again, that's just, both of these exercises are to show you where the calculator is getting its numbers from, so that we're not just blindly going to that menu and having no idea where, how it's coming up with these values. All right, so this is just kind of like a peek behind the curtain. But let's take a look at some problems, and then we'll see how you can use the calculator. It's going to make your life a lot easier in general. Okay. So, does increasing the amount of calcium in our diet reduce blood pressure? All right, so again, I'm not going to read this all out loud to you. You can kind of read it on your own. It's up here on the screen. But the key pieces that we have here is that there were 21 participants in total. They were randomly assigned to two groups. So there's 10 in the calcium supplement group. There's 11 in the control group that are receiving a placebo. The experiment was double-blind, so that's good. The response variable is the decrease blood pressure for a subject after 12 weeks. An increase appears as a negative value. So we want a decrease, all right? We're trying to reduce our blood pressure, but just be aware that the way this data is presented, positive numbers represent a decrease, negative numbers represent an increase. So this says, test whether there is a significant drop when increasing calcium intake. All right. So let's just kind of walk through the process here. So our null is that the two approaches are the same. So we expect the mean amount on calcium to be equal to the mean amount on a placebo. Or we can say that when you subtract the mean of the calcium from the mean of the placebo, or actually, I said that back. When you subtract the placebo from the calcium, we expect it to be equal to 0. Both of those are equivalent. You don't have to write both. You just pick which one you want to write. All right, now the alternative, and again, we have to be careful here because remember, even though it says significant drop when increasing calcium take, remember that positive numbers represent a drop here. So positive numbers are actually a good thing. So when we write our alternative, we're actually going to write that UC is greater than UP because, again, that represents a drop because positive numbers are good in this scenario. And then our alpha, all right, we can set that at 5%. And again, I guess I should just say up here, you could also write this as UC minus UP is greater than 0. Either one of those is fine. You don't have to do both. Just pick one or the other. Now, as far as doing this on the calculator, all right, all of that data that you see there, you're going to want to enter that into stat edit. So I've already done that. So there's all the data in stat edit. Then you're going to go to stat tests, and you're going to do a 2-sample t-test. All right, and again, there's going to be choice between stats and data. All right, when it's on stats, you have to provide the mean, the standard deviation, the sample size, all that information. When you go to data, it just gets that for you. So list 1 is an L1, list 2 is an L2. Frequencies, we're pretty much always going to be leaving those at 1, so you don't really need to worry about those. And then we're testing that we think U1, which again is the calcium group, is going to be greater than U2, which is the placebo group. As I mentioned in the last video, we always pick no for pooled, and then we can go to calculate here. All right. And that'll give us our test statistic. It'll give us our p-value. It'll give us the degrees of freedom that was calculated by that much larger equation. And then it just tells you what the mean was, what the standard deviations were. So there's your two means. Those are your two standard deviations. Those are your sample sizes. So it gives you all of those numbers. So if we look at this quick, the mean for calcium was 5. The mean for the placebo was negative 0.27. So clearly these numbers are different. But is that difference significant? All right, that's what we're testing. Is that a significant difference between those two values, or is it random variation? All right, so again, when you're doing these, you should write out what you picked. So we picked the 2 sample t-test. On this one, there's not a lot to say what you picked because you can just say that I used the data option. All right, I don't really need you to tell me that if you pick data, stat tests. I mean, I'm going to assume that you put it in L1 and L2. I mean, that doesn't really tell me anything. These are always staying 1, so that doesn't really tell me anything. You should just tell me what you picked here, all right? Because if you pick the wrong one, that is going to mess up your answer, so it's good to let me know which one you picked so that if you're getting the wrong answer, I've got kind of an idea of what went wrong. And then again, pooled is always going to be no, so you don't really need to write that down because I'm just going to assume that you left it as no, all right? Just always leave that as no. There's no sort of question on that. All right, so really, as far as work, like as long as you're showing me that, for a data one, that's fine. On the stats one, you'd write out more, but for a data one, that's really fine. And then again, you always want to write out your test statistic, which in this case was 1.6037. All right, test statistic was 1.6037. You want to tell me your p-value, which for this one was 0.0644, and then you want to write a conclusion, which in this case is because our p-value is over 5%, we fail to reject the null. So again, what that's saying is even though x1, the average for sample size 1 was 5, and even though the average for sample size 2 was negative 0.27, what we're saying is that gap is not large enough to be statistically significant. It's close. I mean, the p-value was 6%, but based on what we had, that gap is not large enough to be statistically significant. Now, our sample is pretty small. If we had a larger sample and those results stood up, we'd probably find it to be statistically significant. But based on the experiment we designed, there's not enough evidence to say that this gap is a statistically significant gap. All right, it might just be random variation. And again, if we were worried about that, we might just have to create one with a larger sample size. All right, so again, that's how it's going to work on the calculator. Let's take a look at another one here. So this one says beta blockers. In a study of heart surgery, one issue was the effect of drugs called beta blockers on the pulse rate of patients during surgery. All right, again, you can read the rest of it. I'll just gotta highlight kind of the key information. So we divided it into 2 groups of 30 patients each. All right, one group received the drug, one group received a placebo. We measured the pulse rate. The treatment group had a mean of 65.2 and a standard deviation of 7.8. For the control group, the mean was 70.3 and the standard deviation was 8.3. And then based on this last sentence where it says, see if the beta blockers reduce the pulse rate, that's what we're going to use to actually write our alternative hypothesis. Because again, the null is pretty much always the same. We're just going to say that the mean when using beta blockers is equal to the mean on the placebo. And then our alternative, all right, we're testing to see if beta blockers reduce the pulse rate. So our alternative is that UB is less than UP or mu. All right. So to mix it up, we'll use an alpha of 0.01 this time. All right. Again, 5% and 1% are the two numbers that you usually see. I mean, we've been using 5% pretty much every time, but we'll switch it up to a 1% this time, which means we have a smaller chance of making a type 1 error, but we've increased our chances of making a type 2 error. All right. So again, if we're doing this on the calculator, this time we're doing, well, same as last time, we're doing a 2-sample t-test. Only this time we have to choose, again, never pick z-test. All right, we never pick z-test because we never know the population standard deviation. So we go to 2-sample t-test. This time we pick stats, and we just have to put in the information that they give us. So the beta group, all right, had a mean of 65.2. It had a standard deviation of 7.8, and it had a sample size of 30. All right. The mean for the control group was 70.3 with a standard deviation of 8.3, and it also had a sample size of 30. All right, we are expecting that the beta blocker is going to be less than the placebo group, so make sure you change that over. And then again, pooled is no. So on this one, it is a good idea just to kind of show me what you wrote down or what you plugged in. So x1 was 65.2, S of x1 was 7.8, n1 was 30, x2 was 70.3, S of x2 was 8.3, n2 was also 30. And then I don't need the pooled part because, again, it's always no, but you should write that U1, your testing is less than U2. All right, so then we can hit calculate. All right, we get a test statistic of negative 2.4525. We get a p-value of 0.0086. All right. So there are two means, 65.2, 70.3. We're testing, is the difference between these two means significant? And in this case, our p-value is under 1%, because we're checking it against 1%, because that's what we picked as our threshold value. So because it's under 1%, so let's just put this under 1%. So we reject the null and accept the alternative. So basically what we're saying is, for this one, the difference is significant. All right, continuing on. We're going to talk about Jordan's cat. All right, so Fern 2 is a finicky eater. I don't know what happened to Fern 1, but we're looking at Fern 2. Jordan is trying to determine which of two brands of cat food Fern prefers, Tabacat or Chowline. Great names. For 2 months, she flips a coin each day to decide which of the two foods to feed Fern and weighs how much Fern eats in grams. Jordan is super cool. Here's the data. So 31 days with Tabacat for an average of 85.2 and a standard deviation of 3.45. 30 days for Chowline with a mean of 82.1 and a standard deviation of 4.62. Construct and interpret a 99% confidence interval for the difference in mean amount of food Fern eats when she is offered Tabacat and when she is offered Chowline. Right? So again, if we're doing this on the calculator, we can go to Stat, Tests, and then you're looking for the 2-sample T interval. Again, we never pick 2-sample Z interval. All right, that would require us to know the population standard deviation, and we never know that. So we're going to pick the 2-sample T interval. All right, so let's write that there. 2-sample T interval. All right, we don't have any data, so we're going to use the stats option. And then it pretty much asks for the same thing it asks in the hypothesis test. So our x1 can be 85.2, our S of x1, 3.45, our n1 is 31, our x2, x bar 1, x bar, I should have done that up above 2 because they're averages, so x bar is 82.1. Our S of x2 is 4.62. Our n2 is 30 for this one. Again, they don't have to be equal, and in this case they're not. And then our C level we get from the problem is going to be 0.99. And again, we're not going to be picking pooled. So if we put all of this information in, all right, 85.2, 3.45, 31, 82.1, 4.62, this one's just 30, 30, and then our confidence level is 99%. We're going to leave pooled at no. We can calculate it. All right, and it gives us the output. The main thing that we care about is the interval up top. Again, it tells us the degrees of freedom using the formula. It gives us those individual values that we typed in. But the main thing is the confidence interval, which is 30484 to 5.8952. And again, what this is saying is that we are 99% confident the true difference of Tabacat minus Chowline is between 0.30484 and 5.8952. So it's either super close, like the difference is really, really small, only 0.3 of a gram, or it could be as large as almost 6 grams. But we're pretty convinced that the cat likes Tabacat better, because notice that 0 is not inside of this interval. So one of the possible values is not 0. We're not saying there's no difference because 0 is not inside of this interval. It seems pretty clear that it does prefer Tabacat, but the question is whether it prefers it by just a tiny amount or whether it prefers it by as much as 6 grams. All right, so we've just got one last problem here just to give you one more example of sort of doing a confidence interval. So again, there's a big long description up here about the experiment and what we're testing. But basically, we have two groups. We have a normothermic group and we have a hypothermic group. And the general idea here is if keeping patients warm during surgery reduces the chance of infection, then patients in the normothermic group should have shorter hospital stays than those in the hypothermic group. All right, so constructing 95% confidence interval for the difference between means for the length of stay in hospitals for the normothermic and the hypothermic groups. So we're expecting this group to be lower. All right, here's the data that we collected. There's a sample of 104. The mean was 12.1. The standard deviation was 4.4. Hypothermic, we're expecting the stay in the hospital to be longer. All right, 96 people participated in that group. They had a mean stay of 14.7 with a standard deviation of 6.5. So with our experiment, we observed a difference of 2.6 days, but that doesn't mean the true difference is 2.6. We want to create an interval based off this data to give us a better idea of what the range of possibilities could be for that gap. All right, so again, we're going to do a 2-sample T interval. All right. Again, on your calculator, if you go to Stat, Tests, all right, 2-sample T interval is right there. Again, we don't pick Z because that involves population standard deviation, which we don't know. All right, we don't have any data here. We just have stats. So our X1 is 12.1. Our S of X is 4.4. Our N is 104. Our X bar 2 is 14.7. Our standard deviation for X2 is 6.5. And then our sample size here is 96. Our confidence level for this one is 95%. And then again, we always pick no for pooled. So pooled is never going to be yes. It's always going to be no. All right. And then we calculate. And it will give us that interval. But let's start off just by kind of writing down sort of the different stuff that we want to show as work. All right, so we're doing a 2-sample T interval. X bar 1, we used 12.1. S of X1, we used 4.4. N1, we used 104. X bar 2, we used 14.7. S of X2, we used 6.5. And N2, we used 96. Again, you don't have to write pooled because it's always going to be no. But you should tell me what you used as your C level, which for this one was 0.95. Okay. So all of this gave us a confidence interval of negative 4.162 to negative 1.038. Now, a common question is, what happens if I flip and put all of these x1 values into x2 and take all of these x2 values and put them up in x1? All right, you will get the same numbers. They'll just be positive. Because remember, when we put the normothermic into x1 and the hypothermic into x2, what the calculator is calculating is the interval is normo minus hypo. All right, and because normo is smaller, that's why we're getting negative values here. If we flip them around, then the calculator would be doing hypo minus normo. Hypo is bigger, so you'd be getting positive values. All right, that's why it's important that when you write your statement to kind of say what's happening here, you specify what order you used. So we are 95% confident. The true difference of normothermic minus hypothermic is negative, that's right, is between negative 4.162 and negative 1.038. Right, but again, it's important to specify this so people know what direction you did the subtraction in. All right. Now, if we're putting this in context, what we're basically saying is you can expect to spend roughly between one to 4 fewer days in the hospital. And then another thing to notice is 0 is not inside of this interval. All right, so 0 is not in the interval. So the difference appears to be significant. Because remember, if 0 is in your interval, then we're saying one of the possible values of this minus this is 0. And if that value is 0, that would imply that there's no difference between the two. So because 0 is not in this interval, we can be pretty sure there's a significant difference between the normothermic treatment and the hypothermic treatment. All right, so again, one last problem, one last example here, just so that you can see kind of how these different things work. All right, so I hope these were helpful. And as always, if you have any questions, just make sure you reach out. All right, talk to you later.